Okay, in this lecture, we're going to finish up with our section 4.2 material on the column space and null space of a matrix and how they relate to linear transformations. So this last part of the section will deal with the kernel and the range of a linear transformation, which are directly related to the column space or null space of a matrix. So to start out our section, we'll mention that subspaces of vector spaces other than Rn, so for example, maybe a subspace of a set of matrices or polynomials or a function space can often be described in terms of a linear transformation instead of a matrix. So when we're working with the vector spaces Rn, we're thinking about n-dimensional vectors, and so linear transformations between, say, Rn and Rm can be described by matrix multiplication. But if we're working with another vector space, say a space of polynomials or continuous functions or matrices, we may not be able to describe a linear transformation by a matrix. In this last part of our section, we are going to generalize the definition of a linear transformation, which we had seen in chapter 1 and 2. So a more general definition is the following. A linear transformation T from a vector space W into a vector space V into a vector space W is a rule or a function that assigns to each vector x in V a unique vector which we denote as T of x in the vector space W. So in general, that is a transformation. A linear transformation satisfies the two conditions for linearity, namely that the transformation of a sum of two vectors, u and v, is the sum of the transformations of those two vectors, t of u and t of v, for every u and v in our vector space. And part 2 is the transformation of a scalar multiple of a vector u is equal to the scalar multiple of the transformation of that vector u for all vectors u in our vector space V and for every scalar c. Now, for a linear transformation between vector spaces, say V and W, we would define the kernel or null space of that linear transformation T as the set of all vectors u in the space W, such that T of u, that is the image of u under the transformation T, is equal to the zero vector in our W subspace. Now, the range of T is defined as the set of all vectors in W, which can be expressed in the form T of x for some x in the vector space V. So the range of T is the set of all images of vectors in V under this transformation T. And we can see that these definitions of a kernel or range of a linear transformation would be exactly the same as the null space or the column space of a matrix if we're talking about a linear transformation from Rn to Rm defined by matrix multiplication. In the same way that we had shown that the null space or column space of a matrix are subspaces, it is not difficult to show that the kernel or the range of a linear transformation T are subspaces of the vector space V or W. All right. So as an example of a linear transformation which may not be expressed in terms of matrix multiplication, let's consider the transformation of differentiation that we're familiar with from our calculus courses. So here, suppose that V is the vector space of all real-valued functions f defined on some interval from a to b with the property that they are differentiable and the derivatives of these functions are continuous functions on the interval from a to b. So we're looking at functions f of x, which are defined on a closed interval a to b, and differentiable such that the derivative of the function is continuous on that same interval a to b. And we will let w denote the vector space of continuous functions defined on the interval from a to b. And we will define a linear, a transformation, which we're going to show is linear, denoted as d, which will map from v to w. And this is the transformation that changes a function f in the vector space v into its derivative, f prime in the vector space w. So in part A, we're supposed to show that this transformation D is a linear transformation. So there's two things that we need to show that a transformation is linear. The first of which is that if we take the transformation of a sum of two vectors, in this case our vector space is a space of functions, so whether the transformation of a sum of two functions is equal to the sum of the transformations. So let's think about what this transformation D is defined as. It's the operation of differentiation of a function. So when I'm looking at D of f plus g, if they're functions of x, for instance, I would be differentiating the sum of f plus g. And from our Calculus 1 course, we know that the derivative of a sum of functions is the sum of the derivatives of those functions. That is f prime plus g prime. But the sum of the derivatives would be the sum of the image of the functions f and g under this transformation D, which is defined as differentiation. So here we have shown that the derivative of a sum, as we already knew from Calculus 1, is the sum of the derivatives. Therefore, for this transformation, D of f plus g is the sum of D of f and D of g. Now the next thing that we have to show is that our transformation of a scalar multiple of a vector, let's say c times f, would be equal to c times d of f. Now, the operation that D is performing is differentiation. So we would differentiate the function c times f, but we know from our calculus sequence that the derivative of a constant times a function is equal to the constant times the derivative of the function. So that is c times f prime, which is the image of f under this differentiation transformation D. So since both of these conditions hold, we see that D is a linear transformation. Now, of course, that transformation we could not represent in terms of a matrix, our matrix multiplication, because the spaces are spaces of functions rather than the spaces are in dimensional vectors. Now in part B, we are asked to show that the kernel of the transformation D is the set of constant functions on the interval from A to B. So here, if we are trying to find the kernel of a transformation, we're looking for the set of vectors, or in this case functions, f, such that we get the 0 vector under the image, or as the image under this transformation D. Now here, D is the transformation which gives us the derivative of our function. So say that our function is a function of x, d of f would be f prime of x, and to find the kernel, we're looking for the function such that that image is equal to the 0 vector in the space W, which would be the function which is identically 0. So we know from our calculus sequence, if the derivative of a function is equal to 0, that means that the function f of x is equal to some fixed constant. So here we have the constant functions within the vector space V, and recall that V was the vector space of real valued functions f on the interval from A to B. So we're specifically talking about constant functions on the interval from A to B. All right. So let's look at one last example. In our last problem here, we are considering a linear transformation T from P2, that is the set of polynomials of degree 2 or less, into R2. And this transformation is defined as follows. T of P, so taking some polynomial P, its image under the transformation, is the two-dimensional vector, P of 0, P of 0. So our two components have to equal each other, and they are equal to the value of this polynomial when t is equal to 0. So for this transformation, we are asked to find polynomials p1 and p2 in the set of second-degree polynomials or less, which span the kernel of the transformation T, and we want to describe the range of this transformation T. So let's consider the space P2 that we're mapping from. So here, P2 is the set of polynomials or vectors of the form P of t is equal to a0 plus a1t plus a2t squared, such that each of these coefficients, a0, a1, and a2, are real numbers. So if we're trying to find the kernel of such a transformation, we are looking for the following. We're looking for the set of polynomials, P, such that T of P, which is defined as P of 0, P of 0, is equal to the 0 vector. Now here, for any representative polynomial, P of t, as part of P2, we see if we evaluate this polynomial at t equals 0, well, our a1 and a2 terms disappear, and we are only left with a constant, a0. So we would have something of the form a0, a0, which, to find the kernel of this transformation, we would set equal to the 0 vector. We're looking for the set of polynomials that map onto the 0 vector in R2. So we see here that we're talking about the polynomials where our constant coefficient, A0, is equal to 0. So here, the kernel of this transformation T, or the null space of T, would be the set of polynomials of the form P of T equals A1T plus A2 times T squared, such that the coefficients A1 and A2 are real numbers. So those are polynomials of this form whose constant coefficient is 0. So now that we found the kernel, the problem asks us to find two polynomials, P1 and P2, that span this kernel. So when we look at the form of the kernel of our transformation, we've got polynomials, P of T, which are a linear combination of the polynomial T and T squared. We're just taking a sum of scalar multiples of those two polynomials. So these two specific polynomials, T and T squared, would form a spanning set of vectors for this kernel. So here we can say the kernel of T is the span of the polynomials P1 and P2, which were T and T squared. We saw that every polynomial in that kernel would be a linear combination of T and T squared. So here the P1 and P2 polynomials that we're interested in were these T and T squared values. Now the second part of this problem was to describe the range of this transformation T. So again, let's consider the range of T, which we saw would be the set of vectors of the form P of 0, P of 0, which for polynomials in P2 give us A0, A0. Same expression that we had up here for any polynomial P that lies in P2. So this set of vectors we can think of as a scalar multiple, A0, of the vector 1, 1, where A0 could be any real number. So the range of this transformation T is equal to the span of the vector 1, 1 in R2. So we have described the range of our transformation T as being the spanning set of the vector 1, 1 in R2. So it's the set of all two-dimensional vectors whose components are equal to each other.